Okay, this is going to be the first video in a review, just a brief review of derivatives from Calculus 1. So we're going to go over a couple examples, I think about 5. So here we're going to find the derivative, and if we have negative or fractional exponents, we'll rewrite those as positive exponents, and then rewrite the fractional exponents as their appropriate radical expression. So first thing we're going to take the derivative is 5x to the 7th. There's two derivative rules. One is the power rule, which is the derivative of x to the nth power. The rule there is to bring down the exponent n as a factor and then subtract 1 from the exponent. The other rule that we're going to use here is if we have a constant times a differentiable function f of x, when we take the derivative, it is simply going to be the constant times the derivative of f of x. So when we take the derivative here, okay, the constant 5 is going to be there, and then we're going to take the derivative of x to the n, and we're going to use the power rule, and so you're going to bring down the exponent of 7 as a factor, subtract 1 from the 7, and that's going to become a 6, and we get 35x to the 6. So should be hopefully super easy since you're coming into Cal 2. Okay, so if we mix things up a little bit, what if we asked you to do the derivative of 5 pi to the 7th? Okay, so this is a function of x. Okay, so it looks similar to the previous one, but we don't have an x, we have pi, and pi is a number. So 5 pi to the 7th is just a number. And so if you remember, the derivative of a constant is just going to be 0. The derivative is going to give you the slope of the tangent line. So lines, their derivative is just going to be their slope. And so the derivative of a constant is going to be 0. So you're not going to perform the power rule on this because this is a, this is a differentiable function of x, not pi. Pi is a constant, and we're not treating it as a variable. Okay? All right, so 3 more to go. The next one we're going to look at is the square root of x times 3x plus 2. One option is you can distribute the square root of x through and use the power rule. That's perfectly fine. We'll want to use this as an illustration of using the product rule. Okay. Before we do that, we need to handle the radical notation. So the square root of b, the rational notation is b to the 1/2 power. In general, if you have the nth root of b to the m, you can slide that m out from applying to the b to applying to the entire radical using properties of exponents. And then as a rational exponent, that is b to the m over n. Okay, and then here's our product rules. The derivative of a product of two differentiable functions, okay, and so derivative of f of x times g of x is going to be the derivative of the first function, f of x, so it would be f prime of x times the second function, g of x, plus the first function times the derivative of the second function. Okay, so derivative of the product f of x times g of x is going to be f prime of x g x times g of x plus f of x times g prime of x. And if you have the order difference, you have the f of x g prime of x and then f prime of x g of x. That's fine. Addition is commutative. Also with the multiplication is commutative. So that can be arranged a little bit differently if you want. Okay, so we're going to go ahead and rewrite that as x to the 1/2 power times 3x plus 2, and we're going to go ahead and perform the product rule. So the first function, the x to the 1/2 power, that's a power rule. So we're going to bring down the exponent 1/2 as a factor, subtract 1 from 1/2, which is going to be minus 1/2, times the second function, plus the first function, x to the 1/2, times the second function, so the derivative of 3x plus 2, that's a line, so it's just going to be the slope of that line, which is 3. Okay, and then something you would have done in pre-cal and also in Calculus 1 is factoring out the greatest common factor involving fractions and fractional exponents and negative exponents, and so that's an important skill to clean this stuff up. So we're going to go ahead and get rid of the fraction, which is 1/2, and then the lowest power of x in common, which is x to the minus 1/2. Now, factoring is the opposite of doing like a FOIL or a distributive property, for example. And when you're doing a foiling or a distributive property, the operation is multiplication. So factoring is kind of putting it all back together, and so you're doing the opposite operation, which would be division. Okay, so here's your GCF, 1/2 x to the minus 1/2. And then we're going to take each term. So the first term is 1/2 x to the minus 1/2 times 3x plus 2. And we're going to divide that by the GCF. Okay, and then we're going to simply have 3x plus 2. Okay, and then we're going to take the other term, the x to the 1/2 times 3, divide that by the GCF. Okay, all right, so that's going to be x to the 1/2 minus negative 1/2. Now the exponent rule there is if you have b to the m divided by b to the n, dividing like bases, you're going to subtract the exponent, so b to the m minus n. So that's where we get x to the 1/2 minus negative 1/2. Okay, then we got the times the 3. We're dividing by a fraction, so we'll flip it over and change the operation of multiplication. So instead of dividing by 1/2, we're going to multiply by 2. X to the 1/2 minus negative 1/2, that's going to be x to the 1/2 plus 1/2, which is x to the 2 over 2, which is just x to the first power, and then 3 times 2 is 6, so that becomes 6x. Okay. We'll go ahead and combine our like terms. We have 9x plus 2. Bring down the 1/2, and then you have a negative exponent there, so we're going to write this without any negative exponents. So the exponent rule here is b to the negative n becomes 1 over b to the positive n, so x to the minus 1/2 would become 1 over x to the 1/2, or if we forego that little step there, then that would be 1 over the square root of x, okay? And there would be our derivative. Okay, you can certainly do this also if we clean this up real quick. We can also do this without the product rule. So the point here was to practice the product rule, but since I did mention it, let's go ahead and try it out where we distribute that x to the 1/2 power. So you have you got f of x equals x to the 1/2 power times 3ax plus 2. So you're going to go ahead and distribute that, add the exponent, so you have an exponent of 1 there, so that's going to be 3 over 2 as the exponent, plus 2x to the 1/2 power. Okay, so then when we go ahead and take the derivative, okay, you got the 3 there, bring down the exponent, so 3/2 comes down, and then subtract 1 from your exponent, so it just becomes 1/2, plus 2 times 1/2, x to the negative 1/2. Okay. All right, so then we need to factor out a 1/2 and an x to the minus 1/2. All right, so when we do that, that's going to be, well, if we want to show a little bit of work there, okay, so we'll show a little bit of work. What do we have here? We have 9 over 2 x to the 1/2, and then we divide that by 1/2 x to the minus 1/2. So the fractions would be 9 over 2, flip over 2 over 1, x to the 1/2 minus negative 1/2. Okay, 2 is absorbed, and so we'd have 9x. Okay. All right, it might be a little bit easier to see the second part because this here, when we divide that into there, you're going to be simply left with 2. Okay. Oops. So plus 2. Okay. Let's use correct brackets here. Okay. Doesn't matter if I'm using brackets, parentheses. I just decide to use brackets. All right. So we got the 9x plus 2 here. 2 square roots of x. Okay. And so we still had to factor it to clean it up and look at it. And so it looks nice. And then you can look at where your critical numbers are for the derivative. So it is nice to clean it up. Okay. So 2 more. So number 4 here, we're going to be finding the derivative of the square root of x minus 3 over the square root of x plus 3. When we're doing derivatives, usually it's helpful to rewrite the radicals as rational exponents. So that's where we get those x to the 1/2 powers from. Okay, common error there I see is people get excited and it's not wrong to be excited about math. You know, I find it exciting sometimes. They want to cross those out or cross the 3's out, and unfortunately that doesn't work out. They have to. Everything's got to be factored. You got to have the exact same factor, which we don't have there. So to give you an illustration here with some numbers here, 1.2 is the same thing as 6/5. Okay, now if I wanted to, I could write 6/5 as 4 plus 2, that's 6, over 4 plus 1, that's 5. And then do the 4's cancel? Well, if I'm going to try to do that up there, that's kind of analogous to it. So the 4's would absorb, and I would get 2. And so then I would be saying that 1 is equal to 2, and that's a false statement. So that means our technique is wrong. So we're not allowed to cancel those x to the 1/2 powers, or the 3's would have a similar error. As much as we'd like to, it doesn't work. Okay. All right. So this is a different type of function. It's a quotient of two functions. So we're going to use the quotient rule, which is the derivative of two differentiable functions, f of x over g of x. And then, of course, g of x is not equal to 0. And so that's going to be the low function times the derivative of the top. And so sometimes we say that's low for the low function, d high for the derivative of the high function or the top function, minus the top function times the derivative of the bottom function. And so maybe you've heard before, this is low d high minus high d low, and it's just something silly to try to remember the quotient rule. And of course, just doing some quotient rule derivatives, that'll help it stick. Okay, so it's low d high minus high d low all over the low function squared. Let's go ahead and do that. So the low function is x to the 1/2 plus 3 times the derivative of the top. So that's going to be 1/2 x to the minus 1/2. And the derivative of the minus 3 is 0, so we don't include that. Minus the high function, x to the 1/2 minus 3. I'm sorry. Yeah, it is minus 3. Okay, sorry about that. And then times the derivative of the denominator, and so you're going to do the power rule, 1/2 x to the minus 1/2, and then the derivative of the positive 3 is going to be 0, so we don't include that. Okay, all over the denominator squared. Okay, go ahead and distribute the 1/2 x to the minus 1/2. Then we're going to be multiplying like bases, so when you multiply like bases, you're going to add the exponents. So it's going to be 1/2 x to the 1/2 plus negative 1/2. Okay, and we're just distributing this through. Oops, just distribute that through. Okay, and then plus 3 over 2 x to the minus 1/2. Keep distributing, minus 1/2 x to the 1/2 plus negative 1/2. Okay, and then we're going to have a double negative here, and so that's going to make the final term a positive. So plus 3 over 2 x to the negative 1/2. Okay, notice that this and this are the exact same thing, but they are off by a minus sign, so those are going to absorb. Okay, all over the denominator squared, well, you can go ahead and rewrite the x to the 1/2 power as the square root of x, and then plus 3 squared. Okay, 3/2 plus 3/2 is 6/2, which is 3. X to the minus 1/2. All over the square root of x plus 3, quantity squared, and so square root of x and then plus 3 squared. Okay, and then we can go ahead and send that x to the minus 1/2 to the denominator. And kind of a general rule of thumb, I do not like to multiply out denominators usually, so leave them alone, don't multiply them all out. Maybe in the case where you're rationalizing a denominators where you want to multiply denominators, but in general, leave the denominator alone. Don't try to FOIL it out. It just makes it messier and harder to see what's important, asymptotes, domain, that kind of stuff. All right, one more here. And I know there's a rule for the derivative of tangent, and this is how we get the rule. Okay, tangent is defined to be the sine over the cosine. Okay, and then we'll just put up the derivative formula for quotient again. So derivative quotient is low d high minus high d low all over low squared. So we're going to be taking derivative of the sine. And the derivative of the sine is equal to cosine. And you would have derived that using the limit definition of derivative and some angle formulas in Cal 1. Derivative of the cosine is negative sine. Okay, so and one other identity here. This is a Pythagorean identity. Sine squared plus cosine squared is equal to 1. So that's going to come up quite often a little bit later on in the class. Okay, so take the derivative. So the low function cosine x times derivative of the top, and the derivative of the sine is cosine, minus the top function sine of x times the derivative of the denominator. The derivative of cosine is going to be negative sine, all over the denominator squared, so cosine of x quantity squared. So it's going to be cosine squared x, and then you got a double negative, so plus sine squared x, all over cosine squared x. Also for a reference, 1 over cosine is the secant. So the numerator is the Pythagorean identity. Cosine squared plus sine squared is 1. Okay, so we have 1 over cosine squared x, which is secant squared x. And so you probably remembered that from Cal 1, that derivative of tangent is secant squared. And so this is a pretty easy example to illustrate the quotient rule. Okay, we'll see you next time.